Okay, let's run through some of these questions. So number one says, which of the following contains one fundamental and one derived unit? Well, all of our fundamental units are these right here, right? Kilograms, kelvins, amperes, seconds, moles, and meters, right? KKASMM, which maybe it'll help you. You can remember with the term killer kangaroos, right? KK, are surely murderous marsupials, ASMM, right? Kilogram, Kelvin, ampere, second, mole, meter. So if we look here, there's a few things that don't belong here, right? They're not fundamental. Joule is not a fundamental unit. Newton's not a fundamental unit, and Coulomb is not a fundamental unit. So we need a pairing that has one fundamental and one non-fundamental, right? The non-fundamentals we refer to as derived units. They're derived from somewhere else. They come from somewhere else. So if we look, ampere is a fundamental, and Coulomb is not. So our answer for this one is going to be B. Which of the following will reduce random errors in an experiment? We said this a lot at the beginning of the year, but as we repeat an experiment over and over and over and over and over, right, we're reducing our chances for making random errors or reducing the impacts of random errors. So anytime you want to reduce error, repeating your readings is going to be a good idea. So D. A body accelerates from rest with a uniform acceleration A for time t. The uncertainty in A is 8%, and t has an uncertainty of 4%. So A has an uncertainty of 8, t has an uncertainty of 4, and we want to find V. Well, we know these are all arranged into our formula, A equals V over t, right? We know that formula. Well, if we want to put this in terms of V, let's multiply the t on both sides, and we get A times t is equal to V. Technically, it's change in V, but I'm just going to drop that for right now. So we have AT equals V. Well, let's plug in our uncertainties. 8%, 4% will give us the uncertainty in V. Well, when we multiply percentage uncertainties, we add them. Right, so we're not going to multiply 4 and 8. We're going to add 4 and 8 for a total of 12%. So our answer is 12%. B. Number 4 we did in class. So I'll come back to that one later, actually. Number 5, the time taken for a stone dropped from rest to fall vertically through 16 meters is 2 seconds. Based on these measurements, what is the best estimate for the acceleration of free fall? Okay. So we're dropping this thing 16 meters. That's our distance in 2 seconds. And notice how it says we're dropping it from rest. Right, that gives us one more piece of information. It tells us that our initial velocity is 0 meters per second. And we want to find the acceleration. Well, all of these variables get arranged into s equals ut plus 1/2 a t squared. And this is going to be pretty simple because u is 0, so we don't care about that. This is all going to be crossed out, because 0 times t is going to give me 0. Now I can go ahead and plug everything in. 16 meters for s, right, is equal to 1/2 times a, which I'm looking for, times 2 seconds squared. If I simplify this side, I wind up getting 2a is equal to 16, and therefore 8 meters per second squared is equal to a. So this one you should have gotten B. A volume is measured to be 52 millimeters cubed. The volume in meters cubed is blank. Let's take a look at this one. So it's 52 millimeters cubed, and we want it in meters. Well, we know milli stands for 10 to the negative 3. So if we look at what this is saying 52 times 10 to the negative 3 meters times 10 to the negative 3 meters times 10 to the negative 3 meters, right? Because it's millimeters cubed. So all of that inside of there is being cubed. Now, if we simplify this, 10 to the negative 3 times 10 to the negative 3 times 10 to the negative 3, that's 10 to the negative 9th meters. If we look at my options, though, that's not one of my options, right? We have something close to it. 5.2 times 10 to the 8, which all they really did was move this decimal place over 1, which makes this 5.2 times 10 to the negative 8, instead of 52 times 10 to the negative 9th. So that would be your final answer for that one. This one, the graph got cut off, so we'll skip it. Graph got cut off for number 8. Number 9 we did in class. Number 10, graph got cut off again. Number 11, which of the following may be determined from a speed-time graph? Distance, right? Because if we look, we have speed. Oh, why did I put S? I'll put speed in parentheses so you don't think it's velocity. Speed and time. Let's just say we have a relationship that's linear. Let's say we have like a constant speed, something like that. Well, we know that velocity is equal to distance. Speed is equal to distance over time. Right? So V times T is therefore equal to distance. The area underneath the graph is going to be my distance, so I can very easily find the distance from a VT graph, speed time graph. Displacement is different. Displacement is a vector, right? It has direction, which means I need to use a vector to find it. So I would need a velocity versus time graph. B, distance, right? I'm using a speed time graph. So I can find the scalar quantity because speed is a scalar. I can use a scalar to find a scalar. I can use a vector to find a vector. So 11 is going to be distance. Power, again, is force times velocity, so it doesn't matter for us. And force, I don't know how you would get that out of this. Unless you do the math, maybe. Let's see. Number 13. A skydiver falls 80 kilograms vertically with a constant speed of 50 meters per second. The upward force acting on the skydiver is approximately blank. So we're falling at a constant speed, which means all of my forces are canceling out. Now, if I'm falling down, right, here's some object, it's falling down and has a mass of 80 kilograms. Well, that means the force of gravity, right, Fg, remember, is equal to mg. Going down would be roughly like 800 newtons because it would be like 80 times about 10 meters per second squared. Technically 9.81, but I'm just saving some time here. So 800 newtons of force going down. Therefore, we need 800 newtons of force going up to put this thing in equilibrium, right? Because we're going at constant speed, all of my forces need to cancel. So I have no acceleration. So 800 newtons going up. Number 13 is C. Number 14. A car of mass 1,000 kilograms accelerates on a straight, flat, horizontal road with an acceleration of 0.3 meters per second squared. Right, 0.3 meters per second squared is my acceleration. They say the driving force is opposed by a resistive force of 500 newtons. And also my mass is 1,000 kilograms. They say, what is the net force? Well, they gave us a little bit more information than we need. Right? We know the net force is just mass times acceleration. So this whole idea of the resistive force, that's already being taken into account in this idea of the net force. Right? The total force. I don't care what forces in particular are going on. Right? I could list a bunch of other forces acting on this thing maybe. All I'm caring about when I say acceleration is the net force. Right? This acceleration is caused by the total force acting on the object. And they say find the net resultant force, right? So we want to use this formula, find the net force, which is just, again, mass, 1,000 kilograms, times acceleration, 0.3 meters per second squared. Don't overthink these things, right? If the formula says this is the net force, that's the net force. If the net force is mass times acceleration, it's always mass times acceleration. So 300 newtons would be the net force. So we wind up getting B. Number 15, I believe we've looked at in the past before, which of the following is a condition for a body to be in translational equilibrium? The only thing you care about in equilibrium is that the resultant force on an object is zero, right? Zero total force, so A. The resultant force on the body in any direction is 0. That's the thing you want to look for every single time. In this case, Stephen pushes 2 boxes, P and Q. They stay in contact with a force F of 30 newtons. One has a mass of 2 kilograms, one has a mass of 4 kilograms. They move with a constant speed. The fact that they move with a constant speed tells me that there's no acceleration, right? And as per this formula, if my acceleration is 0, because I'm going at constant speed, no matter what mass I plug in here, I'm going to wind up getting 0 newtons of force. Like, that's just the way the math works out. So constant speed means the total force, the resultant force, is always 0. So A. Which of the following is a correct definition of work? You can jump back to your notes where I put the exact definition, but I think once you do that, it'll be pretty clear that it is the product of a force and distance moved in the direction of that force, right? That's just a definition we kind of need to know. It's not force and distance, it's not force and time, it's not force and displacement. It's force and distance moved in the direction of the force, right? It's very particular. So 17 is B. 18, graph is gone. 19, we only have one option. Thankfully, it's the correct option, right? The power of the engine will always be given by force times velocity, because that is the formula for power. 20 we did in class. 22, which of the following is a correct statement of Newton's second law of motion? Let's see. The momentum of a body is proportional to the net external... Well, it's not going to be a momentum one. I'll tell you that much right now. So we're between forces acting on a body proportional to the mass of the body, and a force acting on a body is proportional to the acceleration of the body. So this is a bit of a weird one, but the answer is going to be D. Right? Let me explain why, though. F equals ma. So we could see that if the acceleration increases, well, then the force is also going to increase. Right? Similarly, if the mass were to increase, the force would also increase. So technically, the force is proportional with both of these, right? It's proportional with mass, and it's proportional with acceleration. In other words, if one goes up, the other one goes up. If mass goes up, force goes up. If acceleration goes up, force goes up. But think about the logic of that, right? A force acting on a body is proportional to the mass of the body. Not quite, right? Because you're not really going to be changing your mass just on a whim. Right? The force is not something the mass is not something really dependent on the force. Right? Or the other way around. Right? The force and the acceleration are really going to be the things that are going to be changing here. The mass is more of just a constant. Right? It's not really going to be changing. It's not going to be increasing. It's not going to be decreasing. So the force acting on the body should be proportional to the acceleration of that body. Right? Because those are the ones that are going to be changing in this formula. Mass is just going to be a constant. It's not really proportional to anything. You're not really going to be increasing your mass. You're not going to be decreasing your mass. It's just mass. It just is what it is. And these ones, I'll make a separate video on, the ones of these, because I want to get the picture in there too. So I'll leave this off right here, and I'll upload this